Well, welcome back everyone to the first afternoon session today. In this session, we're going to continue the theme of smart solutions for shipyards, including smart vessel design. We'll hear presentations from senior experts and industry leaders from Meyer, HTT, BAE Systems, ITI, and Artemis Technologies. And we'll aim to finish this session by 15:10 for an afternoon break and networking. But first up, I'm very pleased to introduce Anthony Laurella, who's a technical pre-sales specialist at Meyer HTT. Anthony's a simulation specialist and is going to talk to us about improving marine performance engineering through digital applications. Over to you, Anthony.
Great. Thank you very much. Hello, everyone. Welcome to today's discussion, as mentioned, around marine performance engineering through digital applications. The topic of focus today, particularly, will be on system simulation, specifically in where it can support the analysis of new ship designs. So, as mentioned, thanks for joining. I'm your presenter today. A little bit of background on myself. I've been a simulation specialist at Meyer HTT in Montreal, Canada, for the past 7-ish years, having a background specifically in system simulation and mechatronic analysis across multiple industries, including marine. A little bit about Meyer HTT before we get into everything. We are an engineering firm with over 30 years of experience, also performing software development and customization of engineering tools, also doing consulting activities in design, simulation, manufacturing, PLM, and having expertise in operational technology, industrial IoT, advanced analytics, and AI. There's a lot more to discover, but you'll be able to find our contact information towards the end of the presentation today. So taking us into our main topic, we'll begin by examining a few of the current challenges which we're facing right now, and then kind of get into how we can address them. So currently, I'm sure it's not new information. We've probably all heard it before, but we're seeing a notable increase in recent years in things like regulations regarding emissions. These types of regulations are driving shipbuilders to consider more and more design options, which previously we were not. Things like hybrid propulsion, full electric, or alternative fuels. And on the flip side of that, on the business side, we're also noticing a reduction in market share as larger shipbuilders claim more and more of the market, either through expansion, consolidation, or through other means. Counter that with the fact that, since we have new technology that's appearing right now and emerging due to kind of the capability of new designs, we have new players who are arriving on the scene, kind of increasing the amount of people that are vying for kind of the now reduced market share. Put all of these factors together and you're facing a lot of complexity. And I think this is showing a real need for innovation as a differentiator, kind of to counter all of this. This is also supplemented, as I mentioned, through the prevalence of industry advancements. More and more, we're seeing that newer technologies are becoming available, or new advancements are making otherwise designs which were too costly or complex or simply infeasible are now becoming much more attainable. And this is through either new technologies or new tools and methods in the design and or the analysis, kind of opening the door to these new opportunities. So let's couple those two facts together and looking at them through them at the previous challenges that I mentioned. It's clear that there's a huge opportunity here for innovation as a response or an answer to those challenges that I mentioned. And right now, with what I said, I think the environment for doing so is well prepared, because of the state of the art let's call it, there are more possibilities right now than ever for variations or innovation on ship design, as mentioned, or even just the possibility of um, validating kind of the behavior of newer ship designs. More complex methods are making what was previously thought unachievable more feasible and more realistic. So the list of what is possible in terms of technologies or methodologies is ever expanding. So, however, being new, they tend to be varied and complex. So where that puts us is, with these new designs or possibilities becomes an increased need for evaluating the designs. This becomes a critical step when we're in innovation. We need a way to understand if these designs are feasible. And so what we're looking for and what we'll talk about today is a way to accurately and quickly assess these designs and understand the performance of the different possibilities in the context of a vessel and also its subsystems. So that takes us to system simulation, which we'll be focusing on today. Here we'll discuss system simulation in a bit more detail and how it fits into the landscape of ship design and performance analysis and a little bit beyond that. So system simulation as a whole allows us to take a very high level look at a vessel or any system really, and all of its subsystems, particularly from a model-based approach. So models can be of, like I said, one simple element like the engine, the transmission, HVAC system, electrical components as well, or these can be put together and look at the entire ship as a whole. The type of analyses which can be performed through system simulation are, we'll say, varied. Ultimately, it's really up to the user. This is a very flexible approach and a very flexible way for opening the door to a lot of possibilities in terms of the types of analysis which can be conducted. We'll explore more of that shortly. Ultimately, the analyses, although varied, are all kind of characterized by being generally very quick to run and dynamic in nature. And this is critical when we're looking at my previous point of having a need for assessing early on, different design possibilities and how feasible they are given different operating conditions. So a great example of this in action is illustrated in the example that I'm showing here, which is the selection of propulsion architecture given a certain kind of operating condition or journey for a vessel. In this case, we have an analyst or a designer who is looking to choose early on between different propulsion architectures. They would have the possibility of a number of different hybrid configurations, full electric, or even conventional combustion. And what's needed here is a way to quickly assess the architectures given the same kind of operating load and understand and draw conclusions as to which ones are going to be feasible or at the very least, which ones are most feasible and worth pursuing in terms of having the most potential. So in this case, this can be addressed via a system model of the ship and all of its critical elements which are necessary for answering that question. In this case, that would be modeling things like the hull and its interaction with the water, propeller, driveline, and also the obviously the propulsion system in this case, which would have multiple versions depending on the ones we want to analyze and compare. And in this case, we're able then to understand the effect in terms of fuel consumption or energy consumed and other things like vessel speed and things like that. So a system model would be able to do this quickly and answer the question very quickly, allowing us to kind of narrow down our selection to the ones which have the most capability and focus efforts there. Ultimately, the earlier we can do this, the better, as we can kind of, like I said, focus the efforts and be more efficient on when we're spending our time. In system simulation, we're using something akin to mostly a lumped parameter approach, and this can be kind of considered different from traditional maybe CFD or FEA analysis in that we can do this before any geometry has been created. We don't rely on any CAD geometry in system simulations. There is no meshing that's needed. Um, you know, and we're more concerned with individual components representing things like the hull, like I said, the propeller, or even the sea state, um, and a few others. Um, Now, system simulation also allows for a lot of customization or user input, embedding results from other tools within these models by using things like response surfaces or lookup tables, as well as supplementing the analysis being performed via kind of scripting and other means. So, in addition to kind of hull propeller modeling, the strength of system simulation really is in the name. It's just that being able to integrate these different subsystems together and understand the interaction as a full ship. So, whole ship modeling, as we can see here, allows us to do a number of things. First of all, assessing the power distribution or the power consumption of different elements. In this case, allowing things like power budgeting over the course of a journey, while including things like hotel loads on the overall ship power system, and understanding how that budgeting will work. Other things we can do is, for example, understand the impact of the operation of one piece of equipment on another over the course of an entire mission. The approach, like I said, is very different from finite element analysis or CFD as well. Mostly in that it allows for a much broader scope of what's being assessed. In this case, we are focusing much more on whole system performance or equipment sizing rather than feature design or concerning ourselves with geometry. Fleshing out what can be kind of the art of the possible in system simulation, I have here also a few examples of other things that can be addressed. Here we can see, for example, cooling systems, 3 degree of freedom maneuvering tests, torsional vibration analysis for the propeller and driveline, as well as a closed loop control for a variable pitch propeller. These kind of, I wanted to share these as kind of an illustrative landscape of what is possible. They're by no means kind of limited to this, but ultimately, what we want to understand is that these models are inherently multi-physics and well integrated together. So beyond just the system models, we also want to talk a bit about the capabilities, and inherently system models are very modular and also very interoperable. What I mean by that is they work very well with the inclusion of data or whole models from other simulation code. For example, we can extend these models to work with 3D simulation by using an open standard called functional mockup interface, effectively embedding one model in another and allowing it to communicate. Capabilities like this means that a system model has a lot of potential to grow as a project expands and maintain its usefulness. So in this example, for example, a CAD model can share information with a number of different tools. For example, a system model can have information coming from a general PNID and understanding the dimensions and scaling there of those tools. Additionally, we can also include data from a separate CFD result of a propeller, for example, into a system model to then inform kind of a much larger model that includes things like the driveline and then assessing the impact on the engine as well, or the whatever propulsion system is selected. So what this means ultimately is that a system simulation model is a great springboard towards a number of other large-scale questions around the design and operation of a vessel. like I had indicated earlier, this is a great way of integrating data from other design studies or analyses and reducing siloed processes when we're going about ship design. So we talked a little bit about kind of the core functionality of system simulation. Here we're going to kind of expand a little bit the scope of the discussion to kind of address that point I made earlier on expanding the usefulness of these system simulation models. Right. We'll take a look at what else can be done and leveraging kind of the lightweight modular nature that I was talking about just earlier. I think the first thing that we can do with a full ship model that in this case would include sea state modeling as well is some route planning. For example, we have the ability in a system model to include data for wind, waves, and other kind of conditions out at real sea conditions. And we can do things like linking this to just general ship advance over the course of the mission, or even GPS coordinates. And so what that allows us to do is, combined with a vessel model, is understand things like max speed, fuel consumption, and route duration as a function of some of the other input requirements. So in this example, for example, we can see a vessel which is undertaking a common route across. Here we can see the Baltic and North Seas. We could run this route at 11 or 13 knots and assess both scenarios. And in this case, the system model of the vessel would contain the propulsion architecture and different variations there. And also a few of the other necessary things like the propeller and hull, like we mentioned before. We could also go a step further, include all of the electrical consumers for the hotel loads for energy budgeting, as mentioned. And then we can make assessments on the different types of propulsion architectures, like I had indicated earlier, but then also compare things like journey, the duration of the journey, fuel consumption, and even extend that to projecting CO2 emissions over the duration of the journey. So moving on from that to a new topic that also extends the capabilities of these system models, we can further extend them by leveraging them in processes like generative engineering. Here we are looking at ways of going beyond our typical approach for exploring design options. Typical design studies, by the time simulation begins for these processes, we're already locked into a limited number of designs, whether we know it or not. We've limited things in terms of architecture selection, just based on what we're considering. By opening things up and using AI-based processes, we can really open the door to all possibilities, even ones that we would not have considered at all. And so here we extend this to ship design. Generative engineering means that each part of the vessel can be considered separately, and we can consider the connection of all of these different parts or subsystems together, but also understand how each one can vary in terms of its characterization. So all of this would be captured and used as a starting point from which we can then generate hundreds or simply dozens, depending on the different kinds of designs from that one initial seed model. And so once the basic architecture is set, it's possible to generate those multiple variations and different configurations, like I said, automatically assessing their performance for given target criteria. And then each of these will be evaluated and ranked. At the end, we can assess the different designs, but also manually intervene and reinforce the process by coming in and understanding, based on our knowledge, what might actually be better, and promote certain designs and further reinforce what is actually a more desirable design than others. So in this case, we're performing generative engineering through the use of computational notebooks, using narrative text and math. Models as code in this case would be integrated, and as you can see here, automating model block diagrams. This kind of provides a means for performing engineering and reporting all at once. The last topic of discussion that I want to get into is another avenue for extending the use of the system models. Here, kind of we're looking at digital twins, and the term digital twin is something that's being used more and more frequently. Ultimately, there's many different versions of a digital twin depending on its intended purpose. Here we're looking at, for example, leveraging a system model in an operational digital twin, where we can leverage things like creating lightweight and portable versions, even lighter weight than the system model by leveraging things like reduced order models. The point of this is to be able to embed these in other processes that would take in real-time data from a vessel using things like telemetry or other data that's being fed in from a vessel in operation, and leveraging the model to make predictions about the state of a piece of equipment that otherwise is not able to be either instrumented or we can't really know anything about through conventional means. So we can take other data from the vessel, feed it into a model, and be able to make decisions on things like the ship operation when we're extending beyond a desirable operating zone, or even conducting things like predictive maintenance, being able to use intelligent models to do this. Another one would be, in executable digital twins alongside the actual kind of real equipment in the field or on site or at sea. And the challenge with, however useful, sometimes the challenge is we're taking in huge amounts of data, generating a lot and terabytes of data. And the challenge ultimately is, with all of this available data, how do you parse it and access what matters and what's important, effectively just kind of separating the wheat from the chaff. This is also something that we can do by addressing these kinds of challenges, by helping to develop the tools to intelligently sort through all of that data and extract relevant parts, and be able to link that to kind of the root causes for certain events. So this is kind of what's beneficial in terms of being able to reuse these models in an executable or operational digital twin scenario. So that takes us to the end for today. I've included here my contact information as well as where we can be reached at Maya HTT. And I just want to thank everybody for your time. And now I'll pass it over, I think, back to you.
Thanks, Anthony. That was great stuff. We don't have any questions in Q&A yet, but I'm sure they'll appear. So I'm going to lead off if that's okay. You've given us a good rundown of a whole raft of different modelling approaches. Can you incorporate cost modelling into that approach to estimate operating costs, etc.?
Yeah, absolutely. So I think that's a capability that would be considered in as post-processing, let's say. We can take some of the data that I was showing there and extrapolate that to operating costs. I think the best case scenario for that would be to take in real-time data of a vessel at sea and be able to understand where we might be seeing cost overrun or risk of cost overrun for a certain vessel.
Great. Okay, good. Thank you. So we've got a question from Amr here from Zamel Shipyard, but he's asking about if you've got three different potential configurations for propulsion system for an OSV, how much time and how much simulation might be required to give us the enough decision data? Did you have any existing case studies?
There are none that I have handy, but I know that, for example, it depends on the scope. Typical engineering answer of it depends, but we've had some that could be turned around in half a day, depending on the available data. It really depends on the scope of the question being asked, and then we can build a model which is what's nice about system simulation, small enough to address only those questions and just have the critical elements for modeling that are needed to answer that. And typically that allows us to be much, much more efficient with the analysis.
tremendous. That's great. So so you talked about being able to extend these models to look at predictive maintenance aspects. What can you expand on that a little bit more? I mean, what sort of I guess decisions or information might that yield?
Yes. So the models themselves can give a lot of information that otherwise is very difficult to instrument on an actual vessel. So we can take advantage of this to understand when a piece of equipment on a ship might be operating outside of typical conditions, and then make projections as to how that might affect the lifetime of the piece of equipment. Right. So if it's operating in a way that would shorten its life, then we can have a model that would be able to understand that and indicate when we might want to accelerate like a maintenance schedule for a piece of equipment, for example.
Of course, got it. Okay. Well, I think we're just about out of time. So, Anthony, thank you very much for that tremendous presentation. And we'll now say goodbye and come back shortly with the next speaker. Thank you.
Thank you very much. Thank you.